And welcome back as we continue our cosmic journey. Let's go ahead and dive into our new topic by starting off by discussing the age of the universe. And so when we start talking about the universe, it's important to kind of think about its movement. Because the realization that the universe changes with time came about in the 1920s and 1930s when measurements of the redshifts of a large sample of galaxies really started becoming available to us. So let's begin with a thought experiment, where we have a universe of a finite size. It's simply just a giant ball of, let's say, 1,000 galaxies. Now, in this ball, all these galaxies would naturally attract each other because of their gravity. If these galaxies were initially stationary, they would inevitably begin to move closer together and eventually collide because of the gravitational attraction. Now, they could avoid this collapse only if, for some reason, they happen to be moving away from each other at relatively high speeds. The problem what happens in an infinite universe is a little bit harder to solve because, it's infinite. But Einstein used his general theory of relativity to show that even infinite universes cannot be static in nature. Since astronomers at the time did not know the universe was expanding, he changed his equations by introducing an arbitrary new term referred to as the cosmological constant. Now, this constant simply just represented a hypothetical force or repulsion that could balance gravitational attraction on the larger scales and permit galaxies to remain at fixed distances from one another. But then about a decade later, Hubble and his co-workers reported that the universe is indeed expanding. So there could be no mysterious balancing force needed in the universe. Now, Einstein himself has reported said that the introduction of the cosmological constant was at the time the biggest blunder of his life. But relatively recent observations indicate that the expansion of our universe is accelerating. In fact, the observations being carried out now are to determine whether this acceleration is consistent with a so-called cosmological constant. So in many ways, Einstein might have been right to introduce this after all. And so let's look at this with the Hubble time. Because if we had a movie of the expanding universe and ran the film backward, what would we see? Well, one of the first things we would notice is that the galaxies, instead of moving farther apart and colliding and getting to the kind of familiar shapes that we see today, would instead be getting closer and closer. Eventually, we would find that all matter was once concentrated into an infinitesimally small volume. Now, astronomers identify this time with the beginning of the universe. Now, the explosion of that concentrated universe at the beginning of time is what we refer to as the Big Bang. And you've probably heard of the Big Bang before, but a better question to ask is, when did the Big Bang occur? Now, we can make a reasonable estimate of the time since universal expansion began. If we measure the speed with which galaxies are moving away, and the distances between these galaxies, we can then establish how long ago expansion began. And this is exactly what Hubble and many astronomers after him needed to do in order to establish the Hubble law and the Hubble constant. Now, the age of the universe estimated this way turns out to simply just be the reciprocal of the Hubble constant. Let's just say we have a Hubble constant of 20 kilometers per second per million light years. Then we find that Hubble time is about 15 billion light years. However, estimates for the Hubble constant are closer to 21 or 22 kilometers per second per million years, which would make the age much closer to 14 billion years, which is a lot closer to what we think our universe is today. But there's still about a 5% uncertainty in the Hubble constant, which means the age of the universe estimated this way is also uncertain by about 5%. Now, this gets into a good question of the role of deceleration, because the Hubble time is the right age for the universe only if the expansion rate has been constant throughout the time since the expansion of the universe first began. In calculating the Hubble time, we've assumed that the expansion rate has been constant throughout all time. However, it turns out that this is not a good assumption to have. In fact, you probably have heard that the universe rate of expansion is increasing. And astronomers expected at first that the rate of expansion should be slowing down. One of the ways of thinking this, like why the universe might be slowing down instead of running faster as we see it today, is that, well, all matter creates gravity. And that means all objects are going to pull on all other objects, and gravitation is going to effectively act as a brake over time. Now, the mutual attraction between galaxies was expected to slow as the expansion of time passed. This means that if gravity were the only force acting, then the rate of expansion must have been faster in the past than what we see today. If this was true, we would say the universe has been decelerating since the beginning. Now, deceleration would largely depend on the influence of gravity, and that the rate of expansion should be slower now than it was in the beginning of the universe. However, what we find instead is a universal acceleration. Because astronomers spent several decades looking for evidence that the universe was decelerating, but they were not successful in their quest to do so. Now, in order to prove or disprove this either way, they needed two things. First, they needed larger telescopes so they could measure the redshifts of more distant galaxies, and a very luminous standard bulb or standard candle, that is, some type of astronomical object with a low luminosity that produces an enormous amount of energy and can be observed at distances of 1 billion light years or more. Now, we of course have talked about these standard bulbs before, and this was the Type 1a supernovae that were determined to be very excellent standard bulbs. Now, if the universe was decelerating, we would expect that these faraway supernovae to actually be brighter than expected. The slowing down of the universe would actually keep them close to us. But what we found out is that they were fainter, which at first seemed to make no sense. So then the question was posed, what if the universe wasn't decelerating? What if the universe was actually doing the opposite and was accelerating? So if the universe is expanding faster now than it was billions of years ago, our motion away from the distant supernovae has actually sped up since the explosion first occurred, sweeping us farther away from them. Now, the light of the explosion must travel at a greater distance to reach us than if the expansion rate were constant. And the farther the light travels, the fainter it appears. This conclusion would explain the supernova observations in a very natural way, and this has now been substantiated by many additional observations over the last couple of decades. It really does seem that the expansion of the universe is accelerating, and this notion was so expected that astronomers at first resisted considering the possibility that our universe was accelerating away from itself. Particularly the question, how can the expansion of the universe be speeding up? Because typically when we are accelerating, some source of energy must be supplied to accelerate the object in question. In this case, we're talking about the expansion of the universe. Now, the discovery of acceleration was really shocking because scientists still, to this day, have no idea what the source of the energy is. So scientists call whatever is driving this expansion dark energy, which is a clear sign of how little we understand it. Now, one possibility is that dark energy is the cosmological constant that Einstein first created, and this is often associated with the vacuum of empty space itself. Now, keep in mind, when we talk about dark energy, this is not the same as dark matter, because dark matter is simply just an existence of matter that we have no ability to measure with our current technology, because there's no light, no emission. Whereas dark energy seems to be this force that is driving it apart. It's not matter, but something completely different. Now, whatever dark energy turns out to be, we should note that the discovery of the rate of the expansion has not been constant since the beginning of the universe. Really kind of complicates the calculation of the age of the universe itself. Now, very interestingly enough, the acceleration seems not to have started with the Big Bang, because during the first several billion years after the Big Bang, when galaxies were close together, gravity was strong enough to slow the expansion. But as the galaxies moved further apart, the effect of gravity weakened. And we found that several billion years after the Big Bang, dark energy actually took over, and that's when expansion began to accelerate. And so if we look at this with a visual representation, we can see here in this image that a period of very rapid expansion happened at the beginning. We call this inflation, so we can see that down here represented at the very beginning, going from this infinitesimally small volume to spreading out. And again, at this time, the galaxies were very close together, and their mutual gravitational attraction actually slowed down the expansion. But after a few billion years, when galaxies were farther apart, the influence of gravity began to weaken. Dark energy then took over and actually caused the expansion of the universe to accelerate to what we can see here in our present day. And so lastly, let's just talk about comparing some ages within our universe, because we now have one estimate for the age of the universe from its expansion. And it's good to ask the question, is this estimate consistent with other observations? Because the universe should at least be as old as the oldest objects in it. If it's not, that means that something is wrong with our model. And one of the things that we turn to are those globular clusters in our own galaxy for answers. And of course, we can see globular clusters in other galaxies, but ours, of course, is right in our backyard. And one of the things that we can do is look at the models of the interiors of globular star clusters and find out that they have improved over time, providing us with better information about how atoms absorb radiation as they make their way from the center of a star out into space. Second, observations of satellites have also improved the accuracy of our measurements of the distances to these clusters. And what we can conclude is that the oldest stars in the globular clusters typically have formed somewhere between 12 and 13 billion years ago. Now, the globular cluster stars probably did not form until the expansion of the universe had been underway for at least a few 100 million years. Accordingly, their ages are consistent with the 13.8 billion year age estimated from the expansion rate.